Okay. 34 off of the night before homework, is that what you said? So we're on page 113, right? You said 34. In example 2 of this section, we show that the derivative of y equals square root of x is a function with domain 0 to infinity. However, the function y equals square, so we're talking about y prime has this domain. However, the function y equals square root of x itself has a domain of, yeah, no, well, yeah, not last night, but the night before. Right. So it could have a right-hand derivative at x equals 0. Prove that it does not.
I wouldn't understand why it would. The way a root function looks like it would have a right-hand derivative.
It doesn't exist below, though. Like, it doesn't, if you have this, it says prove that it does not have a right-hand derivative. So what happens at this point? And we're looking at, we can't have derivative at the endpoint like that. Well, I would argue that it's not the right-hand derivative that doesn't exist, but the left-hand derivative that doesn't exist, right? How could, there's nothing on the left. It can't come from the left, right? 34.
Okay.
I'm going to show you today. I'm going to show you how to do it on the calculator.
Well, why is it saying prove that it does not have a right-hand limit?
I think you should. Yes, brand new.
Wait, so.
I mean, like,
I don't think so. What else? What else from that? Was there another one you wanted to talk about?
I didn't like get
The derivative doesn't exist there. 42. F of x equals x squared when x is less than or equal to 1. It is hot in here today. Find the derivative of x when x is less than 1. So f prime of x when x is less than 1. That answer is not, oh, yes it is. Yes it is. All right, so the only thing I can do is the difference quotient, right? Which other one? The alternate? You could. You could. So I'm talking about this because I'm talking about when x is less than. You put it into what?
Yeah, I plug in my always gotta do the letter.
Why? Okay, so f of x plus h is x plus h squared, which is x squared plus 2xh plus h squared. These, if you haven't noticed, by the time you get to the end of the questions in each section, you're really into some conceptual type stuff. They get harder. You square each end and then multiply them together and double it to the middle.
No, I mean, like, how do you put the 2x? Oh, that's what the 2x came from the lower portion.
Minus x squared over h, the x squareds are gone. I have 2xh plus h squared over h. an h goes from everybody, and so I end up with 2x plus h. If I'm going to 0, that's gone, so 2x.
I heard my name. Never mind.
Okay, that makes sense to me, you know what I'm saying? But what about the bottom?
So is the answer, how is the answer 2?
Well, it said when x is less than 1. So part B asks you for the derivative when x is bigger than 1.
Wait. Are we just getting that answer right there?
Yeah, f prime of x when x is less than 1 is 2x.
And then 2x shows up right. Or is that
That's just coincidence. Yeah, no. So now if I do f prime of x when x is greater than or equal to 1, what? Today, hopefully. Hopefully we get to it today. I want to show you how to graph on your calculator, and then we're going to move on. I'm going to skip the rest of this section. There's a lot of things that are included that are not really tested on, that it's just not worth confusing you on. Yeah. Derivative when x is bigger than 1, so that is 2x, right? So I want the limit. So this is f of x is 2x. As h goes to 0 up, f of x plus h minus f of x over h, which is h to 0, sorry. 2, I'm putting x plus h here. So 2 times x plus 2 times h minus 2x over h. Boom, 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 boom. F of x plus h is 2 plus h, which is 2x.
Oh, because you have a variable in front of you.
Correct. F of x is 2. So this is 2. So look what we found here. This is pretty interesting. The derivative of a quadratic is linear. And we know, remember when we were graphing, and if we started with the parabola, we said that it's got the derivative there is linear. And exactly. What do you think the derivative of a cubic might be? A quadratic. Okay, we found if f of x is x squared, f prime of x was 2x. We found that if f of x is 2x, f prime of x is 2. The derivative of this quadratic is linear. The derivative of a linear is a constant. What do you think the derivative of a cubic would be? A quadratic. What do you think the derivative of a quartic would be?
Cubic. And that's it. There's no more functions.
There are more, but I'm just saying. What are you doing? How are you finding it?
Just like a pentatonic. Oh, are you just going down, like in complex?
Yes, you're going down 1 degree. 1 degree down. Find the limit as x approaches 1 from the left of f prime of x. All right, so this one is when x is less than 1. This is when x is greater than 1. So what is the limit as x approaches 1 from the left of the derivative?
So that would be the left of 2x.
Which one's to the left?
The bottom one.
But you're looking at the derivative.
So 2.
It's 2x.
2.
So it's 2.
How do you know it's 2 again?
Okay, because look.
What the left of the derivative.
Can we graph?
F prime of x, right? And so that's the derivative. 1 from the left. 1 from the left would be this one because it's less than 1. So I'm looking at this derivative. So really I'm talking about what's the limit as x approaches 1 from the left of 2x. So you can just plug in.
Plug in negative, no, 1.
1.
Mm-hmm.
I guess, thank you. How about the limit as x goes to 1 from the right? It would be 2 again. The limit as x goes to 1 from the right of the derivative. So now I'm in this equation, but no matter what x is, y is always 2. I know, that was really bad.
Wait, so what are you saying?
Okay, wait, continue.
Blue stuff you just wrote. Can you say that?
The limit as x goes to 1 from the left of 2x. From the left and right is the same, so it's 2. You plug 1 in. And then from the right, same thing of f prime of x. From the right, I'm using this equation, but it doesn't matter.
I did the limit as x approaches 1, and I like worked through with the alternate. And I got 2. Oh my god. So like how?
Well, that's what it was 2 for both of them.
Yeah, but I think I know.
I feel like the alternate formula does overcomplicate it, in my opinion.
I had a whole lot.
But if you're just evaluating a limit and not a derivative, just plug in if you can. All right, other questions? Oh, I'm sorry.
I actually like that.
F says to use the definition to find the left-hand derivative of f at x equals 1 if it exists. So the left-hand derivative at 1. So I'm looking for f prime of 1 from the left side. Right? Isn't that what it means? Use the definition to find the left-hand derivative of f. So the derivative at 1, but from the left. Which way is from the left? Right? But I'm not going to use the squared. I'm sorry. I'm going to use the x is less than 1. Yeah. So I got 2 times 1, which is 2. And then the right side, the right-hand derivative. Right. Well, wait, because what is, yes, oh, it's the same. But I need to check continuity, right?
Did you try?
It has a whole.
There might be no.
What happens? What happens here? Does the function itself, if I just look at the function, is it continuous at the
No.
point 1?
No, because it has to be.
If you plug 1 into the first one and 1 into the second one, you don't get the same thing, so it's not continuous, right? If I plug in f of 1 here, I get 1 squared, which is 1. If I plug in 1 here, I get 2 times 1, which is 2. Yeah, it's exact. It is a piecewise. It's a piece of a parabola and a piece of a line.
It's differentiable, but not.
No. It's not differentiable because it's not continuous. And we're going to talk about that theorem a little bit today. Just because it's continuous does not mean it's differentiable. But if it's differentiable, it has to be continuous.
So there's no. Wait, no, I'm not gonna have that.
We're like,
Yeah.
Oh, I'm sorry. Yes, the limits exist because the left side and the right side are the same. So the limit exists there. Use the E. Does the limit as x approaches 1 of the derivative exist? Not of the, yes. Not the limit of the function, but the limit of the derivative. And so if you take the derivative there, so I've got 2 derivatives, right? I've got 2x. This one is when x is less than 1. And 2 when x is bigger than 1. Is that continuous at the point 1? Yes. And it's 2. Both sides, if you plug in 1 for x, you're going to get 2. This was a tough question.
I actually like this question now because
Say again. So G, I would say that it fails to exist, but not because of the one-sided derivatives, but because of the continuity issue there. And part H, I think G and H kind of go together. The derivative does not exist, again, because of that continuity issue. Anything else from the night before homework that we didn't have time to get to? How about last night's homework? Several of you said you had a couple questions. Okay, the graphing of 4. Yes.
I don't have a lot of work for the 5. There wasn't any work for the 2. Wait, you can do that for 3, 4, all of them.
This is number 3 that looks this way.
Well,
All right.
It was a quarter, so I was like, oh, it can't write that.
All right, so it kind of does. This says compare the right and left-hand derivatives to show that the function is not differentiable. And if you look at it, as you come in from the left, right, I'm coming in on the top of this quadratic, and as I come in from the right, I'm coming in on a linear function here. And those values are not the same at all. The left-hand side of the derivative and the right-hand side of the derivative are not the same there. Right. So it's not differentiable because the left-hand side, and you don't really have to go into, I mean, other than the slope of the parabola is not the same as the slope of the line at that point.
So what do you say?
I would literally say that. The slope of the parabola and the slope of the line at x equals 1, or the slope of the square root of x at that line are not the same. No, it did not.
And it worked out. I mean, it worked, but like, I didn't
it was
understand.
proven.
I didn't see what we had to do right now.
Okay.
What number?
So you did, this is square root of x, and this is 2x minus 1. So you did, the limit as h goes to 0 of each one there at x equals 1. I guess that's technically the algebraic way to justify it. Yes.
And then you're going to realize that there's slopes not the same.
So f of x plus h minus f of x over h. And I'm going to do it for, I'm going to do it at x equals 1 for the square root of x and for 2x minus 1. That's where the point P is. The point P is 1, 1. Should have done x equals 1 for number 2 because it says P is 1, 2. You sure it didn't go h to 0? Okay. That's that difference quotient. Y'all want me to work through this one algebraically? Okay. This is number 3. Let's do square root of x first. Square root of x would be the square root of x plus h. So this would be h goes to 0 of square root x plus h. Oh, this is a nasty one. Say that again. Oh, you are correct. So now you've got the limit as h goes to 0 of the square root of 1 plus h. You're still going to have to, by root 1 plus h plus 1. You're going to have to do that conjugate we talked about. And this will, more than likely, you will have somewhere on that exam where you're going to have to do something along these lines of some type of algebraic manipulation or conjugation like this. Yes, when you see a square root and you need some type of manipulation, automatically go to a conjugation and see if that'll work. This would be 1 plus h. The middles are going to cancel minus 1 over h.
Oh, so when you do that, it just gets rid of the square root.
Yeah. Gets rid of the square root, and the middles will cancel out, because that'll be plus root minus root, and then you multiply that last one together. And then you got to h. This would be a 1 there. So it would be the limit as h goes to 0 of 1 over the square root of 1 plus h plus 1, which would be 1/2 exactly. But then you got to do the other function there. So you'd have to do the difference quotient again. By the time we finish this and you learn the shortcut, you should be pros at the difference quotient.
Okay, so I should say.
Allison, you okay? Y'all good?
I'm just going to try to do this one graphically.
I'm sorry, I misread this one. This one you did need to do algebraically, though, man. Yeah. Because it said to compare the left and right hand limits. I misread this one and jumped right on. Okay, so 5 through 10 are the ones that you tell is it differentiable and what kind. Let me show you the other side quickly. It's a little easier. It's 2x minus 1 at x equals 1. So it's the limit as h goes to 0 of f of 1 plus h minus f of 1 over h. F of 1 plus h. I always come out here to decide if there's anything even remotely complicated about it. It just helps me see what's going on. 1 plus h. And f of 1 would be 2 times 1 minus 1, which well, this is a linear, so this is a little bit. Well, I've been doing it a lot longer than you. Not much longer, though. Not that much older than y'all. Thank you. H over h is, you know, the left side and the right side are not the same. Josie, you okay? You don't feel well, do you? Sorry. Y'all are a tough crowd. What else from your homework? I'm going to do you like my second one. Hello, So Hungry. I didn't know your name wasn't Aaliyah. I didn't know it was So Hungry. Hi, this is So Hungry. Yes. And y'all wonder why my patience has run thin by the end of the day. Four.
I know what to do. I just like don't know how to.
Oh, Lizzie. Okay. Another difference quotient.
No, I know how to do that. I know how to get to the limit of expression 1 over x plus h.
All right, let's do number 4 together. This is number 4. All right, we have y equals x, and we have y equals 1 over x. And for this one, p is 1, 1. I'm testing the derivative from the left and the derivative from the right. The y equals x is from the left, the 1 over x is from the right. So I am going to do the picture. You know how to do the x one. Let me still just do it because I'm OCD, and if I leave it up here without having it complete, I feel really bad about myself. 1 through 4, you should have done it algebraically, but the others weren't algebraic.
How'd you know that x was 1?
Because it says the point P is 1, 1. So 1 plus h minus 1 over h, don't, that leaves me with 1, right? But then 1 over x, so now here's the hard one. 1 plus h minus f of 1 over h. So f of 1 plus h is 1 over 1 plus h, yes? Say yes, because that's right.
Yes, ma'am.
Thank you. F of 1 is 1, so I have the limit as h goes to 0 of 1 over 1 plus h minus 1 over h. I'm going to make these have common denominators, so I'm going to do 1 plus h over 1 plus h. So up here, I end up with, so I've got the limit as h goes to 0 of 1 minus h, because this negative's got to go through here, right? It's got to distribute. Over 1 plus h, but hang tight because I still got this h in the bottom, so I'm going to multiply by 1 over h. What? The top of this was 1 minus 1 plus h. I had to get common denominators of 1 plus h. You get the third part. Right here. This part?
So I have 1 over plus h minus 1.
1 over 1 plus h minus 1 over h. Okay. All right, so this is 1 over 1, right? So I'm going to give them a common denominator of 1 plus h. And if I multiply it to the bottom, I'm going to have to multiply it to the top. So 1 plus h over 1 plus h is the same thing as 1. Do you agree? And do you agree now that they both have the same denominator? 1 over 1 plus h minus 1 plus h over 1 plus h. Right, Van?
Got it there.
All right, so now if you combine the numerators, you have 1 minus 1 plus h over 1 plus h, right? And that's how I got to this numerator.
And then,
So now I have negative h over 1 plus h times h.
okay, how is there's another h in the bottom?
I remember that very bottom h?
Oh.
I multiplied by 1 over h. Yes, I'm going to do that next. I'm still going to 0. So yes, Van, I would cancel this h. Remember, it's holding its place with a 1. That's right. Well, I plan on showing you some of the shortcut today. We'll see how it goes.
So it would just be -1.
Yes, differentiable. So it's just -1. But the whole point of this was showing that this and this are different. So therefore, the function is not differentiable at the point 1, 1. Woo!
Sorry, I didn't have to do that.
No, it's okay. Don't lie, man.
It's just a lot. She's probably getting extra day to spend.
I fumbled it out.
That's probably my fault because I told you just look at the graph. I didn't read the question adequately enough. Yeah.
Is there a way to write non-differentiable like with numbers?
Graph the derivative of what? Oh, no, you don't have to do all that. For 11 through, what'd you say, 16? All you had to do was graph those. Which one? Number 8? Yes, so number 8, and on these, so it looks, it is something like that, and it says over the closed interval here, which happens to be from whatever this is to this, a is the function differentiable at every point. No, it's not, right? Because I see multiple things that are going to cause problems in differentiation. What do you see that's not going to be able to be differentiable? Okay, non-differentiable. I'm going to put ND because I cannot find the derivative there because it is a whole. It's a removable discontinuity. Where else do you see? These? Is that 0? Yeah. Why there? Two reasons there. It's a discontinuity for one, and for two, the left and the right side derivatives do not match. Right?
The slopes are positive.
Exactly. And then there's a corner. What else? That's all. So is the function continuous? No, it's not continuous at all. There are multiple points of discontinuity. Discontinuity, discontinuity, yes? Is it neither continuous nor differentiable? That would be correct because it's not continuous and it's not differentiable. And when we say not differentiable, we're not talking about a whole. It's asking us to look at the function as a whole. Is it continuous on all points in its domain, and is it differentiable on all points in its domain?
So whenever it's asking that, it wants you to look at it as a whole, not.
Sorry.
Whenever it asks you, is this differentiable on all domains? You want to specify whether it is or just say no.
No, if it's not differentiable, it depends on what it asks. It'll say if not, where is it not differentiable? And then 11. So 11 asks you, the function fails to be differentiable at x equals 0. Tell whether the problem is a corner, a cusp, a vertical tangent, or discontinuity. So the inverse of tangent, so if you think about the way tangent looks like this, right? And this was a calculator problem, so you definitely could have graphed it. But it looks something like this. And this is 1, and this is -1, and there are asymptotes. This is inverse tangent. But it says where x does not equal 0. So I got a hole right here. It does kind of look like a cube root. And then it says when x is 0, y is 1. Y is 1 when x is 0. Okay? So that's what this piecewise function looks like. Let me just write this if you don't have your book out. This is number 11. Inverse tan of x when x does not equal 0 and 1 when x equals 0. So the directions say the function fails to be differentiable at x equals 0. That's not in question. They're telling me at 0 it's not differentiable. They want you to say why is it not differentiable. Is it a corner, a cusp, a vertical tangent, or a discontinuity? It's a discontinuity here. There's a hole there, right? Yeah, so it's a hole. It's a discontinuity. You might think, well, because it's piecewise, that's more than likely what it's going to be. If you know that it's not continuous.
Could it be 2?
What you mean? 2 what? 2 what?
2 of the 4. Yeah, it looks like it's
You think that it's a vertical tangent? Okay, so the reason it's not a vertical tangent there is because the inverse tangent is not defined at 0. You see what I'm saying? So that knocks that out, even if you thought it might be. It could be a discontinuity in something else. No, they're just going to be 1. It does. It looks like that cube root, but here there's a hole in the graph. No. Yeah. Can I have a discontinuity? Anything else? Anything else? I think y'all probably did. Y'all have a tendency to do that. Let's take a brain break for just a second before we. Let me get out my little.
using calculator for smiley face.
Yay.
I'm ready to rumble.
I'm ready. I am going to use my little All right. Let's say. What? Let's say I want to find the derivative like the one we were doing. What were we doing before? We had the function x squared, and we're just going to do a really easy one. And we said, what is the derivative at 1? Right? And we did the difference quotient, and we found that the derivative was 2x, and then if we plugged in 1, we found that the derivative at 1 was 2. So the slope of the tan line at the point x equals 1 of just this. So we found it. Here, if I were to draw the tan line at 1, I would find that the slope of that tan line would be 2 there. Okay? And that's what we did before. But I want to show you how to use your calculator to find these, because sometimes things get bleh. And maybe it's a calculator question that you're asked to find the derivative at a point and you don't remember how to do it. You can use your calculator to do it if it's a calculator problem. All right. Proceed. All right. Here's what we're going to do. And you might want to write these down. These steps. Yeah. I mean, it's not hard. It's just. So I'm going to do that same example, basic example, and I'm going to show you 2 ways you can do it. If you go into math and you scroll down to number 8 in deriv. Hit enter. The first thing you're, oh man, I wish I had a, because this is not, I need to use a calculator like y'all's instead of this one.
Wait, that's what mine was.
You can borrow mine. Mine?
Yours probably.
You want mine? It looks like the house.
Lizzie, this is what yours looks like, but that's not. Let me borrow yours.
Argument. There's an argument.
No, that's a fancy one.
All right, in deriv. Oh, yours does it too. Do y'all all have 84s or do y'all have 83s?
I have 83.
Okay, let me show you on both of them. On the 84s, I can use mine for the 84s. I have an 83, y'all. I know. Well, this is not the one that I would prefer to use. The 83. I love the 83. My 83 took me all the way through college until my last year of my last semester, and he made me buy an 89. I was so mad. Believe it or not, 9 times out of 10 in your classes, you can't use your calculators anyway. Okay, but with that said, y'all, I took AP Calculus in high school, and so, I mean, obviously, whenever I passed the exam, I didn't have to take the first level of calculus. But even in Calculus 2, and part of, like, Calc 3, I knew what was going on because AP Cal gave me such a great foundation. I'm telling you. Okay. Okay, I'm going to show you on that one just a second. If you have an 84, you'll want to put an x here for d dx. You'll want to put the function, so this would be x squared. And down here, x equals, we said it x equals 1. And hit enter. Okay? You stick, it should be d dx. That's take the derivative with respect to x. Now, that's for the 84. For the 83.
Wait, what do you do? X equals what? Look, everybody, it's always calculator. It's 2.
I did 1. So I didn't do x squared.
That's at a specific point. That's at a specific point, yes. But now, okay, most of your derivative questions are not going to be calculator. This, remember I showed you an easy one. The ones from your homework are like, use your calculator to find the derivative of negative cosine x at the point x equals there.
So on the derivative,
That's the slope at 1. Yep. That's what we already found. All right, if you're on the 83, your math, same option. Okay, you're going to put the function, so x squared. You're going to do a comma. This is where you're going to put your x. Where we put the x at the beginning on the other, we're going to put the x here. So that's the variable that we're taking derivative of. And then at the point that you want to, okay, so the x goes second instead of first. The function goes first this way. And then this is the point that you want to take the derivative at. Okay?
Do you mind if I
Now.
say something?
No.
Wait, can you write something down? Like,
Let me show you something cool.
can you write like a quick thing, like, I was like, map, directions.
Whoa. What the cow?
Hey, you put the panel in the shop.
Ah.
Mr. McGee, look, you put the panel in the shop.
I'm tripping. How does that work? There is alternate reality.
Put the panel in the shop.
Man, reset it. I want to see it. That is crazy.
Where does that go, y'all?
It goes to.
Into what realm does that go?
Can I jump
Oh
in there?
my God, I'm freaking out right now.
It's Neverland or whatever.
I'm about to run into this. It goes.
Do it, Red.
I want to run into it.
Let's go. If we go at the same time, we can make it in there. Are you ready?
On your mark,
Homework trio.
get set,
We'll do our.
go.
Oh, she moved it. We got
All right.
close to beating
Wait,
it.
Missy, can you write down like a step-by-step thing?
Okay, so yes.
Or you could write like a form, like an entering format. So like the point of So what do we
So in deriv, you do f of x, whatever your function is, right? Then you do x, and then you do your value, whatever that value is that you want to find at that point. Yeah.
Is the second one for 84 always x squared?
I'm sorry, what?
L-I-V.
Yeah.
The difference was it's A-C-U-T-A.
I don't know why this pulled up a chart, but is this always x squared?
You're going to use this to find the answers.
That's always x squared?
Yeah. No, that's always whatever the function is that you're
So if
finding
the function,
derivative
so like
of.
the f of x? That's, but why is this chart up here? It wasn't up here the first time I did it.
Why are you in the table?
I went to math, and then I went down to deriv.
Okay, wait. Okay, now, math. All right. With that said, that's pretty easy, right? Putting it in. Okay. It will also graph the derivatives for you. Oh. Yeah. Wait. Watch. All right. Wait till you see the shortcut tomorrow. It was going to be today, but all right. Oh no, this is how to do it on a calculator. This is not the shortcut.
Oh my gosh, you can do it on your
So yes, if you go in, let's say, remember, the derivative of x squared, we found out, not at a specific value of x, but just in general, the derivative was 2x, right? If I go, that's a line, right? Same thing, go into y equals math in deriv. And this time, in deriv, same thing, same thing.
Oh, we're graphing it.
X equals, and you're just going to have an X there. So if you're in the in deriv with the this way, it's going to be your function X, and then you're just going to put another X here instead of a value.
Wait, can you go back to the graph?
That's the derivative of x squared. That's what it graphs the derivative.
Can you go back? That's so cool. No.
Oh, I'm sorry. I'm sitting here going back on my thing, and
So I graphed the x squared, and then I just did x, comma x.
that's exactly right. That is the derivative of x squared. Because remember, the derivative of a parabola is a line. Yep. What's the? We said the derivative of. Gosh darn it. The derivative of a cubic should be what? A parabola. So graph it and see. What does the graph of a cubic look like? It's a parabola. So you can also graph the derivative.
It's like, if it's x squared, it's like x. I thought, I don't think I would.
Yeah, the derivative is always one to
I know, that's crazy.
Y'all are so silly. Okay, questions about graphing it or using your calculator? Because I got one more thing to show you.
So what's x to the 5? Hold on, so whenever you're calculating the parabola, whenever you want to see what the derivative of a cubic is, you put x to the oh, x cubed.
Have y'all? Go ahead.
You put x cubed, comma, x squared.
No, comma x, comma x.
Okay, gotcha.
Have y'all thought about the terminology and the vocabulary that y'all are using now, as opposed to when you first walked in the door? I think it's so cool to think to hear how y'all talk now about derivatives and functions. We'll watch it again, and then you'll know a little bit more. Huh? It is. It's so cool because y'all walked in and it's all this it's not like algebra where we just building a little bit on it. It's brand new stuff, and y'all are having intellectual conversations with me about these calculus things, and it's so cool. Okay. I get really excited. Well, I have one more thing to show you. I have two theorems I want to talk to you about. I've already talked about them, but I just want to put them in words for you. So not to go back to geometry or anything, but there are theorems as we go through different things. The first theorem I want to tell you about is exactly what I said about being differentiable and continuous. Differentiability implies continuity. Not vice versa. In other words, if it's differentiable, it has to be continuous. That's one of the requirements of differentiability. But you can have a continuous function that is not differentiable at that point.
Like
What am I?
This is like when a rectangle is
The corner, the cusp, the vertical, those are all continuous functions, but they're not differentiable at this point. So even though they're continuous, they're not differentiable. But if it's differentiable, I can assume that it's continuous. Does that make sense?
Right there.
Looks like a bird.
Oh, God.
All right. The other is one that we haven't really talked about, but it makes sense, as does a lot of the type of theorems here. This will come up as we go. This is a theorem that comes up all the time. It's the intermediate value theorem, IVT. If there are 2 points on an interval, I think how I can put this in. If A and B are 2 points on F, and F is differentiable, then the derivative of F will have every value between f prime of A at some point on there. And I'll do an example and show you what I mean, because this is what did you say? Oh, I thought you said no. So I was going to say, it's not hot in here, Lizzie. It's calculus. I do too. I hate it.